Evaluate the double integral. X runs from -3 to 0. Y runs from 0 to the square root of 9 minus x squared, x dy dx. I'm going to do this problem in two different ways. One way is going to be just as a normal double iterated double integral, and one's going to be as a polar coordinates integral, and we'll see that we get the same answer. Let's do the polar coordinates integral first. So so we need to convert to polar coordinates. Let's just, so we're going to know we need bounds on theta and r. We need to draw the picture before we do anything else. So right now, our bounds are x runs from -3 to 0, y runs from 0 to the square root of 9 minus x squared. Okay, so we are over here. It's going to be this quarter circle right here. So the y is equal to square root 9 minus x squared. If we square both sides, we get y squared is equal to 9 minus x squared. That's x squared plus y squared is equal to 9. This is a circle of radius 3 here. So that's why I said this is quarter circle here. So x is from -3 to 0. Oops. To 0. Y runs from 0 to the boundary of the circle. And so this gives us absolutely beautiful, beautiful, easy, simple, constant is really the adjective I'm looking for here. Bounds on theta and r. Theta runs from, this is theta is equal to 0, theta is equal to pi over 2, theta is equal to pi. R is going to run from 0 to 3. So very nice constant bounds here. So our answer is going to be so our integral, theta runs from pi over 2 to pi, r runs from 0 to 3 of, we need to change x here, x becomes r cosine theta, and then don't forget the extra factor of r dr d theta. And so now we just have to evaluate this double integral. The bounds are constant, and I think we can just factor this integral. Theta runs from pi over 2 to pi of cosine theta d theta times r runs from 0 to 3 of r squared dr. Because why can we factor this? The integrand can be written as r squared times cosine theta, of a function r times a function theta, and the bounds are constant. So that's what allows us to get away with this. Okay, let's see here. Antiderivative cosine theta will be sine theta. Plug in pi over 2 to pi times antiderivative r squared is r cubed over 3. We'll plug in r as 0 to 3. And what do we end up with? This will be sine pi minus sine of pi over 2 times 3 cubed over 3 minus 0. And this will be 0 minus 1 is -1 times this is 9. So -9 is our final answer. And I should say it makes sense that we're going to have a negative answer here. We're integrating x on this region. X is negative on this region. So the fact that we end up with a negative answer makes sense. For purposes of comparison, I promise that we do this in rectangular coordinates. So let's just go ahead and evaluate this integral. We're integrating with respect to y first. Antiderivative x is with respect to y. It's just going to be x times y. We'll plug in y from 0, the square root of 9 minus x squared dx. And let's see here. So we end up with x times square root of 9 minus x squared dx. And at this point now, it looks like we're going to want to use substitution. So a substitute in, u is 9 minus x squared, du is negative 2x dx. So du, so negative 1/2 du is x dx. So there's our negative du over 2. And we end up with u to the 1/2 times negative 1/2 du. And our bounds are now, when x is negative 3, u is 9 minus negative 3 squared is 0. And when x is 0, u is 9 minus 0 squared is 9. So our final answer is going to be negative 1/2 times u to the 3/2. Divide by 3/2, multiply by 2/3. Plug in u, runs from 0 to 9. And so this is going to be negative 1/3 times 9 to the 3/2 power minus 0. And yes, that is negative 9. So everything checks out. So two different ways to solve the same problem, roughly, equivalently difficult. Here we have to do substitution. Here, if we put in the upfront work to convert this to polar coordinates, it did make our evaluating the integral a lot simpler.